We have an example problem here. In the circuit below, I is 0.65 amps and R is 5 ohms. What is the value of the EMF? Meaning the battery voltage. So we know these resistances. That one is 5 ohms. Since these two are listed as 2R, these would be 10 ohms each. This current is 0.65 amps. Now we can determine how these are all connected by following a path. If I start at the positive end of the battery and start going through, I must pass by that 5 ohm resistor, but then I reach a junction here. At that junction, we could go this way, or we could go this way. Ultimately, this path we're taking could represent some current. We can talk about the battery current or total current that flows. That would flow through R. But as soon as we reach this junction, some of it goes through this middle resistor, and some of it comes through the path that takes it through this right-hand side, which they've told us this current. These two currents come back together at this bottom junction and become the total current again, headed back to the battery. So we can write an equation that describes what's happening to the current at that junction. The total current's coming into this top junction. It continues on as what I called I1 and as I, this 0.65 amps. So we have a relationship between I1 and the 0.65. Now, in the path that we follow, we did have to pass through the 5 ohm resistor. We had to pass through R, but then we had a choice to go through either one of the 2Rs. So both 2R and 2R, they're the same, they're in parallel. We know this because we do not have to go through both of them when we follow a path from one end of the battery to the other. If they are in parallel, we can find an equivalent such that we could say, well, we don't need to find an equivalent, but I'll finish my thought process really quick. We could say that we would then have just R, and then we would have this equivalent over here, which then would come back to the battery. But I don't need to do that. The reason why is because in parallel, I know they must have the same potential difference. This 0.65 amps, even though the arrow is drawn on the bottom, I know that current had to flow through the top resistor, down this side wire, and then to the left. So this top resistor has the 0.65 amps flowing through it. For resistors, we know the potential difference can be calculated from I times R. So if we plug in that current and then multiply by the resistance, which is 10 ohms, we find that delta V is 6.5 volts. Okay, I'm going to do some erasing here. Hopefully that doesn't throw anyone off. So we now know there's 6.5 volts for this resistor, But that means there's 6.5 volts here as well because they're in parallel. They have to have the same voltage. Using what we mentioned before, now for this resistor, I know it is 10 ohms. I know it has 6.5 volts. So the I1, the current flowing through it, using the same equation but solving for I, we know current is potential difference over R for a resistor. So 6.5 divided by 10. I1 is also 0.65 volts. Sorry, 6.5. Oh dear. 0.65 amps. Right here. So the total current, representing the current that comes out of the battery and back into the battery, is just 0.65 plus 0.65. So the total current that is flowing is 1.3 amps. Now we're still not done. We're trying to find the battery voltage. But now, if I know the current up here is 1.3 amps, and I know the value of the resistor, delta V across this resistor is going to be that current times its voltage, which is another 6.5 volts. Since we have double the current but half the resistor, now we can just follow our loop. If I follow a loop, this battery voltage, as I follow a loop around, that battery voltage has to be shared amongst the resistors we pass by. The battery passes by R, so delta V of just R, and then it passes by 2R. So that battery voltage has to be 6.5 volts plus 6.5 volts. So this battery voltage is 13 volts. In order to make the current in this circuit 0.65 amps. So we end up seeing problems that are similar to the capacitor problems that we had in series and parallel, and needing to use conceptually what has to be the same in series, what has to be the same in parallel, and then using the same equation over and over again for each individual resistor. We didn't need to find this equivalent resistance because we could reason through knowing in parallel they had to have the same delta V, and I saw we had enough information to find one of them, which means we then know the voltage for the other. So I'll do one more example as well, where we will end up needing to use the equivalent resistance, and we can work from there.